Good evening, sir.
Yeah, good evening. Yeah. Could you see the screen sharing, Ajay?
Yes, sir.
Yeah. Yeah. In this session, we will see the concepts of the diffraction and the concept of the polarization. Okay. Suppose if I consider the source of light here, this if I consider the source of light, you know that the source of light is going to send a light rays in the straight direction. Whenever it is going to be incident on the slit, you can notice that some refraction is going to get, the ray is going to bend at the edges. At the edges, the ray is going to bend, and that bending will give rise to some geometrical shadow here. Geometrical shadow here. This phenomenon is what we call as the diffraction of light. Diffraction of light means it is just the bending of light around the corners of an obstacle. And this can be noticeable only if the size of the aperture is almost comparable with the wavelength of light. If the aperture and the wavelength of light are almost same, then there will be a bending of light is going to take place. After bending, you can notice some geometrical shadow over there. That phenomenon, we call it as a diffraction of light. So what is diffraction of light? The phenomenon of bending of light around the corners of an obstacle and its encroachment in the region of geometrical shadow is called as the diffraction of light. You can see the concepts here. This is the light rays which are going to be incident on the slit. At the edges, the ray is going to bend. It is going to bend like this. After bending, it forms a shadow here. This phenomenon is what we called as the diffraction of light. Only you can notice this diffraction if the width of this slit is almost comparable with the wavelength of light. The slit width and the wavelength should be almost same comparably. Then only the diffraction is going to take place. There will be two types of diffraction. One is called as the Fresnel diffraction. The another one is called as the Fraunhofer diffraction. One is the Fresnel diffraction. The second one is called as the Fraunhofer diffraction. In the case of the Fresnel diffraction, you can see that the source and the screen are placed at the finite distance. The distance between the source and the screen are at finite distance. We can measure the distance between the source and the screen. There will be a finite distance between them. If the source and the screen are placed at the finite distance, then whatever the diffraction is going to take place, that diffraction we call it as a Fresnel diffraction. They have given example, the diffraction which is taking place at the straight edge, narrow wire, or with a small opaque disk. And please remember, whatever the wavefront we are getting in the Fresnel diffraction, whatever the wavefront we are getting in the Fresnel diffraction, that wavefront is going to be either spherical or a cylindrical. So what type of wavefront we are going to obtain in the case of a Fresnel diffraction? Either it is a spherical wavefront or it is going to be a cylindrical wavefront. Spherical wavefront or a cylindrical wavefront is the wavefront obtained in the case of Fresnel diffraction. And also please remember, whatever the analysis we can made in the Fresnel diffraction, the analysis is going to be a very complicated one. It is not an easy method. So to analyze the Fresnel diffraction, it is very complicated. Analysis is tough. But in the case of a Fraunhofer diffraction, the source and the screen will be at infinite distance. There will be an infinite distance. Example, you can take the diffraction through a single slit or a double slit or a diffraction grating. Even diffraction grating is an example for the Fraunhofer diffraction. So in the case of a Fraunhofer diffraction, the source and the screen are placed at the infinite distance. And whatever the wavefront we are obtaining in the Fraunhofer diffraction, the wavefront is going to be a plane. So what type of wavefront is going to be obtained in the case of a Fraunhofer diffraction? In the case of a Fraunhofer diffraction, the plane wavefront is going to be obtained. The plane wavefront. But comparatively, analysis is simple. In the case of Fraunhofer diffraction, analysis is simple compared to Fresnel diffraction. So in the case of a Fraunhofer diffraction, analysis is simple compared to the Fresnel diffraction. So you can notice the diffraction through a single slit. You can notice the diffraction of light at a single slit. Now, in the case of a single slit, the slit separation is nothing but small d, and we are going to obtain the interference at the center as bright and some alternate bright and dark in the case of an interference. In the same way, the diffraction also consists of maximum intensity at the center. At the center, you are going to get a maximum intensity. This is what we call as a principal maximum. What is this called?
So principal maxima.
Yeah, principal maxima, which also you can call it as a central maxima. But later, the intensity start decreasing. It start decreasing. It won't get the same type of amplitude like interference. But in the case of interference, almost all bands are of equal amplitude, equal intensity. But in the case of a Fraunhofer diffraction, the intensity decreases as the order increases. As we move away from the central, the intensity and the amplitude start decreasing. And after getting the maximum intensity at the center, at this position, you are going to get a minimum intensity, where intensity is 0 here. This is called as the first minima. What is that called? First minima. After getting the first minima, you are going to get once again a maximum amplitude, but not same as the central maxima. This is called the first secondary maxima. It is called as first secondary maxima. Yeah, the same interference, like we have a diffraction pattern. This is the diffraction pattern. You can see here at the center, the intensity is maximum. The intensity is maximum. This is called the first minima. Then this distance is called as the width of the central maxima. The distance between the two first minima. The distance between the two first minima on the either side. The distance between the two first minima on either side is called as the width of the central maxima. What is the width of the central maxima formula? 2 times of lambda divided by small d. Please remember, lambda is the wavelength, small d is the width of the slit. Width of the slit. In this, you have two formulas. One is 2 times of lambda capital D by small d. The another one is only lambda by small d. What is that difference, Ajay? See here, when I am talking about the principal maxima or central maxima, this is the portion of principal maxima, right?
Yes, sir.
Then this angular separation, this is linear separation. This is called linear separation. This is the angular separation. So, in the case of the principal maxima, there will be both angular separation as well as the linear separation. Angular separation is given by 2 times of lambda by small d. Linear separation is 2 times of lambda capital D by small d.
Yes, sir.
So this is the linear width and this is the angular width of the principal maxima. So how to calculate the angular width and the linear width of the principal maxima? Angular width will be just 2 times of lambda by small d, and linear width will be 2 times of lambda capital D by small d. That is the linear and angular width of the principal maxima. So after principal maxima, what you are going to obtain? First minima. This is called the first minima portion. This is called the first minima portion. And there will be a condition for the maxima and minima. There will be a condition for the maxima and the minima. Now, what is path difference d sin theta called? Path difference d sin theta is equal to n lambda. This is the condition for the minima. So to obtain the condition for the minima, what is the path difference must be equal to? Path difference d sine theta must be equal to n lambda. Path difference d sine theta must be equal to n lambda for minima. Similarly, the path difference d sine theta is equal to 2n plus 1 into lambda by 2. This is the condition for maxima. So what is the condition for the maxima? Path difference must be equal to 2n plus 1 into lambda by 2. What is the condition for the first minima? D sine theta must be equal to n lambda. When n is going to varies like 1, 2, 3 in both the case. When n is equal to 0, this should be a principal maxima. So please remember this condition, Ajay. Path difference d sine theta should be equal to n lambda for minima, and d sine theta should be equal to 2n plus 1 into lambda by 2 for the maxima. Now,
Sir,
you
that's
can,
the path difference, sir.
yeah, tell me once again.
Sir, that's the path difference.
Yeah, path difference,
Yes, sir.
yes.
Yes, sir.
So you can see the differences between interference and diffraction, but that will not what you call help for the competitive exams. But you can notice some of the differences. In the case of interference, always we required how many sources? We require 2 coherent sources, right?
Yes, sir.
But in the case of the diffraction, we can get only one source is
So one
sufficient.
source. Yes, sir.
With one source only we can get the diffraction. But in the case of interference, all fringes is having same intensity, right?
Yes, sir.
All fringes are having same intensity. But in the case of a diffraction, the intensity will decreases as order increases. Intensity decreases as order increases.
Increases, sir.
Yeah. And all fringes are equally spaced. But in the case of a diffraction, the separation between the two bands are not same in the case of diffraction. Got it?
Yes, sir.
Yeah. After this, before going to polarization, you must know the meaning of limit of resolution. Limit of resolution. Now, I'm going to consider the 2-point objects. This is A and this is B. You can distinguish these 2 points.
So
You can see the 2 distinct objects. No,
yes,
A
sir.
is
Yes,
here,
sir.
B is
Yeah,
here. You
A
can,
is there and B is
yeah,
there. Yes, sir.
you can clearly identify the 2-point objects, right?
Yes, sir.
Now I'm going to bring these 2 points objects still closer, like this. Still you can notice, right?
Yes, sir.
Still you can notice the 2-point objects.
Yes, sir.
Still I will bring them closer. Still you can notice 2-point objects.
Yes, sir.
Now I'm going to write the 2-point objects here. Can you notice the 2-point objects in the last case?
No, sir.
No, because it looks like a single point. Actually, this is going to looks like a single point, right?
Yes, sir.
So to distinguish the 2-point object, there should be some minimum separation. That minimum separation only we call it as what?
Sir, limit of resolution.
Yeah. So what is limit of resolution? Limit of resolution is the minimum separation between the 2-point objects for which they are just resolved, for which they are just distinguished. You can distinguish the two close point objects. To distinguish the two close point objects, there must be some minimum separation. That minimum separation, we call it as the limit of resolution. Once again, that separation may be in the form of angle or it may be in the form of linear. If it is an angular separation, it will be 1.22 lambda by capital D, where lambda is the wavelength, capital D is the diameter of the objective. If it is linear separation, it is given by 1.22 lambda divided by 2n sine theta. N is the refractive index, lambda is the wavelength, theta is the semi-vertical angle. So what is limit of resolution? Limit of resolution means it is just the separation between the 2-point objects for which they are just resolved. Either it may be a linear separation or an angular separation. If it is a linear separation, it is denoted with the dx, and if it is an angular separation, it is denoted with d theta. Yeah. Ajay, I'm going to write the 2-point objects here. This is one, this is one.
Yes, sir.
Now you can notice the 2-point objects.
Yeah.
Yes, sir.
Yes, sir.
Now I'm going to consider the 2 more point objects like this. Now, Ajay, can you distinguish the 2-point objects?
Yes, sir.
Okay. Now, I'm going to write 2-point objects, Ajay. Can you notice these 2 points?
Yes, sir.
Yeah, you can notice this, Ajay, but I can't notice. I can't notice this. I'm looking this as a single point object. I'm going to look this as a single point object.
Yes, sir.
So, my ability in the instrument, your ability in the instrument are definitely different. Because you are saying that in this box there are 2-point objects. But I am saying that there is only 1-point object, there are no 2-point objects. So the ability are different between me and you. So the ability of the instrument which distinguishes the 2-point objects is what we called as the resolving power. What is that called?
So resolving power.
Resolving power. So resolving power is the ability of an instrument to distinguish the 2 close point objects. And please remember, this resolving power is the reciprocal of limit of resolution. It is the limit of reciprocal of limit of resolution. Now, can you tell me how the resolving power is going to vary with wavelength? How resolving power is going to vary with the wavelength? I mean, it is directly proportional or inversely proportional? Because you can see the limit of resolutions. You can see the limit of resolution. That limit of resolution is directly proportional to what? Wavelength.
Wavelength, sir.
So, resolving power and limit of resolution are inversely proportional, right?
Yes, sir.
So, definitely this has to imply what?
Sir, they're inversely proportional.
So, either it is in the linear case or in the angular case, resolving power is inversely proportional to the wavelength. Usually, if it is an angular separation, we will call it as a telescope as the instrument. If it is linear, then we call it as a microscope. So we are going to talk about the two instruments. One is with respect to telescope, or the another one is with respect to microscope. For telescope, it is 1.22 lambda by capital D. For microscope, it is 1.22 lambda divided by 2n sin theta. So this is the concept of the limit of resolution in the case of telescope and in the case of microscope. Come to the meaning of the polarization. Actually, polarization is the property of a light. Because of this property of a light itself, we can get the vibrations of the molecules in one single plane. You can get the vibration in a single plane because of one property which we call it as what? Polarization. Polarization means it is the property of a light. Because of that property of light, the light particles are going to vibrate in a single confined plane. Suppose if the vibrations are in all the directions, it is vibrating into the board, it is vibrating out of the board. So all possibility directions are there. Vibrations are all going to move in all the possible directions. If the vibrations are almost going to be in all the direction, then it is said to be an unpolarized light. It is said to be unpolarized light. So what is unpolarized light? Unpolarized light is the one where the light particles are going to vibrate in all the directions, in all possible directions. Then it is called as an unpolarized light. Suppose if the vibrations are going to vibrate in single plane, then we will call it as a polarized light. So what is polarized light? Polarized light is the one where the vibrations of the light particles are in one plane. If the vibrations are in the single plane, then we'll call it as a polarized light. These are the symbols for unpolarized light. You can show the both dot as well as an arrow mark. If you represent dot as well as an arrow mark, that represents what type of polarized light?
So unpolarized light.
So unpolarized light is the one where the light particles are going to vibrate in all the directions. Suppose if the light particles are vibrating in only one plane, then we will denote only with arrow mark like this. We won't put any dot, or we are going to put only the dot. We won't put both arrow mark as well as the dot. If arrow mark was there, only dots are there, then we say that it is a polarized light. And where the light particles are going to oscillate in the plane, that is what we called as the plane of oscillation. So what is plane of oscillation? The plane of oscillation is the one where the light particles can oscillate. The plane which is perpendicular to the plane of oscillation. For the plane of oscillation, if you consider a perpendicular plane, that is called the plane of polarization. So I mean to say like this. In the x-axis, if the light particles are vibrating, you consider one plane perpendicular to that x-axis. Perpendicular to that x-axis. Then this plane where the light particles don't have any vibration in this plane. So in the plane where the light particles will not vibrate, that plane only we call it as what? Plane of polarization. But please be careful. This plane of oscillation or plane of vibration and plane of polarization are mutually perpendicular to each other. Plane of vibration and plane of polarization are going to be perpendicular to each other. And there is some device which we call it as a polarites. What is the job of this polarites actually? This polarites will just convert the unpolarized light into a polarized light. So the process of converting that unpolarized light into a polarized light is what we called as the polarites. So polarites are the devices which converts unpolarized light into polarized light. We are going to use some crystals here to convert unpolarized light into a polarized light. This is very important. Usually the competitive problems are going to be based on this Malus law. What is the statement of the Malus law?
So
Yes, Ajay.
so for this, so what is the use of this Malus law, sir?
If you are converting the unpolarized light into a polarized light, how much of intensity is converted? We cannot convert the 100% of
Yes, sir.
unpolarized light into a polarized one.
Yes, sir. Yes,
So how
sir.
much intensity is going to be measured is
Yes,
going
sir.
to be got in the case of Malus law.
Yes, sir. Understood,
Yeah.
sir.
Suppose if you consider this is the unpolarized light. If this is an unpolarized light, You can convert this unpolarized light into a polarized light. If I naught is the intensity of the unpolarized light, after converting the polarized light, the intensity will be always equals to I naught by 2 into cos squared theta. I naught by 2 into cos squared theta. What is the theta? Theta is the angle between this polarizer axis and the analyzer axis. Angle between the polarizer axis and the analyzer axis. The same Malus law can also be written like this, just I naught cos square theta. When you have to write only I naught cos square theta, if the incident is polarized one. If the incident is unpolarized,
Yes, sir.
then the intensity of the emergent polarized will be I naught by 2 cos square theta. If the incident is polarized, you have to write only I naught. No need of writing I naught by 2. When you have to write I naught by 2?
So only
When the incident light is unpolarized.
yes, sir. Instant light is unpolarized.
Yeah. If the incident light is not unpolarized, it is polarized, then you have to use only I naught. Please remember
Sir.
this.
Yes, sir.
These are the two difference. Next concept. This is also very important. That is Bristol's law. Before going to explain the concept of the Bristol's law, can you tell me these concepts? This is one interface. On the interface, I'm going to incident the ray of light, which I'm using both the dot as well as dot. If I'm using both the dot as well as arrow mark, what type of light it is?
So unpolarized, sir.
It is unpolarized. Now I'm going to draw one normal here. After normal, you can see that the reflected ray is completely polarized. The reflected ray is completely polarized. If the reflected ray is completely polarized, then the angle of incidence, that is theta p. This theta p is called as the polarizing angle. What is the theta p called?
So polarizing
Angle.
and
What is polarizing angle? It is the angle of
so
incidence.
yes, sir.
It is the angle of incidence for which the reflected ray is completely polarized. This
So
reflected ray is
polarized, sir.
completely
So for
polarized.
this, so and for this, the instant ray will be unpolarized.
Yeah, this refracted ray is unpolarized.
Yes, sir.
Even incident ray is unpolarized. So when you incident the unpolarized light, the reflected ray will be get polarized. So for what angle of incidence that reflected ray gets completely polarized, that angle we call it as a polarizing angle. So what is polarizing angle? It is the angle of incidence for which the reflected ray is completely polarized. Now you can notice this diagram, Ajay. This is incident ray, right?
Yes, sir.
This PQ is incident ray. This incident ray is having both arrow mark as well as dot, right?
Yes, sir.
So it is what type of light?
So unpolarized.
Yeah. Look at the reflected ray QR.
Yes, sir.
It is completely polarized, right?
Yes, sir. Only dot is there.
Yeah. Then what is this angle called I'm talking?
So that will be the polarizing angle.
That will be the polarizing angle. This is also polarizing angle, right? Because you know that angle of incidence is equal to angle of reflection, no?
Yes, sir.
Angle of incidence is equal to angle of reflection. Angle of incidence is equal to what?
Angle of reflection.
Angle of reflection. Loss of reflection. Angle of incidence is equal to
So angle of
these two are equal, no? Angle of incidence is equal to angle of reflection, no?
yes, sir. Yes, sir.
But you look the refracted ray, QS. QS. It is completely polarized or unpolarized?
Sir, unpolarized.
Yeah, it is unpolarized. What is this angle called, Ajay?
So that will be
Angle of
sir,
refraction.
angle of refraction, sir. So yes,
Yeah.
sir. So angle of refraction will be equal to polarizing angle, sir.
No.
Sir, okay, sir. Yes, sir. It won't be equal, sir, because it's a
Because the
refracted ray.
medium has changed, the direction will
Yes, sir.
change, no?
Yes, sir. Yes, sir. Yes, sir.
Yeah, like this. Now, this reflected ray and refracted ray are also mutually perpendicular. Please remember, whenever the ray of light is incident at polarizing angle, whenever the ray of light is incident at the polarizing angle, the reflected ray and the refracted ray are mutually perpendicular to each other. 90 degrees. Now, you can conclude theta p plus 90 plus r. Theta p plus 90 plus r equals how much?
Sir, theta p plus r is equal to 90.
Yeah. What is r?
So 90 minus theta p.
Can you apply the Slen's law for this?
Sir, yes, sir.
Can you apply the Slen's law for
Yes,
this?
sir. Sir, yes, sir.
Yeah, apply the Slen's law.
So sin A by sin of 90 minus theta p is equal to mu.
Sin theta p by sin
Yes,
r.
sir. Sin theta p by sin 90 minus theta p is equal to mu.
Yeah, you can write that also. In the place of R, you can take it as 90 minus theta P. What is that sine of 90 minus theta P? Cos theta P. So what is sine theta P by cos theta P?
So tan theta.
So tangent of the polarizing angle is equal to what? Refractive index, right?
Yes, sir.
Tangent of the polarizing angle is equal to refractive index. This is what we called as the Bristol's law. This is what we called as the Bristol's law. So what is Bristol's law? Tangent of the polarizing angle is equal to what? Refractive index.
Refractive index, sir.
Yeah. You can notice here, refractive index and polarizing angle are directly proportional. If the refractive index of the medium is more, the polarizing angle also increases. More refractive index, it will be more polarizing angle. But in the previous chapter, we have given the relation between the refractive index and the critical angle. How that refractive index and the critical angle are related? Refractive index is directly proportional to polarizing angle.
Yes, sir.
But refractive index is inversely proportional to critical angle. More the critical angle, less the refractive index. More the critical angle, less the refractive index. Yeah. I'll write one more diagram for you. This is one polarized. In this, I will write unpolarized light. Now, after coming through this tourmaline crystal, it is completely polarized, right? Because this is
Yes, sir.
polarized.
Yes, sir.
And I'm going to rotate this polarite. If I naught is the intensity of the unpolarized light, please remember, after emerging from this polarite, the intensity will become I naught divided by 2. I naught divided by the 2. So whenever the unpolarized light is incident on the polarized, after emerging, the intensity will become off of that. I naught by 2. I naught by 2. Now, I'm going to use one more polaroid here. This will be the axis. This axis will be as it is initial one like this. This angular separation I'm going to give 60 degree. Can you tell me what will be the intensity coming here? Now this is incident on the second polaroid. But the second polaroid is tilted by what angle? (60°). Now what will be the intensity of this? Use the Morse law.
Yes, sir.
Which is the incident one? I naught by
So
2,
I
no?
naught by 2, sir.
Incident is I naught by 2 into cos squared.
Yes,
Theta.
sir.
What is theta?
So theta is 60.
What is cos 60?
So 1 by 2.
1
So
by 2
1 by
square.
4. Yes, sir. So 1 by 4, sir. So I naught by 8.
So the intensity will become I naught by 8. So this type of problems may be come for the competitive from Morse law. So we can take up the problems in the next class, Ajay, because it is not ready. I think it is not in that PDF format. So this is the theory concepts of the diffraction and the polarization. So in the next session, I will take up the problems on this diffraction and polarization. I think one session is enough for the problems on this. After that, immediately we'll go with another chapters, that is a simple one, that is dual nature of matter and
Yes, sir.
radiation.
Yes, sir. Yes, sir.
But that chapters are very simple actually, Ajay.
Yes, sir.
The dual nature, atom, nuclei, semiconductor. What are the 4 chapters are there? All these 4 chapters are quite simple. We can
Yes, sir.
finish it off that very easily without that
sir.
too much of headache.
Yes, sir.
Okay. So tomorrow
Yes.
we'll continue with these problems. Okay.
Yes, sir.
Yeah. Thank you. Bye.
Thank you, sir. Bye, sir.